Hi there. Today we're going to look at two concepts, geological time as well as radioactive half-life. In geology, there are two ways that we can find the age of something. One way is through comparison, and we call that the relative age, where we say one thing is older than another or younger than another. And this is a less exact method. For example, I might say I'm older than the grade 7 students that I teach, but younger than the headmaster of my school. That's relative aging. However, absolute aging is an exact method. So, in that case, I might say that using absolute terms, I would give my exact age. I am 40 years old. My grade 7 students are 12 years old, and the head of the school would be maybe 50 years old. And that's using absolute terms, which is exact. So let's talk about an example of one way geologists use relative dating. This is called the law or theory of superposition, and it says in undisturbed strata, which are layers of rock, the layer on the bottom is oldest and those above are younger. So it might look like this. Rock layer A is the oldest, the middle rock layer B is second, and the youngest rock layer would be layer C. Same idea if we found fossils in there. So these fossils, trilobites, would be older than these clam fossils. So this would be sort of a method of giving a relative date to the age of things. Let's look at this layer of rock. So these are different layers of lava flow and sill. And so which layer of rock here would be the youngest? That's right, layer 4 would be the youngest, and layer 1 would be the oldest according to the theory of superposition. Now sometimes magma, as you know, can get up into the crust, and we call that an inclusion. So an igneous intrusion might come into a sedimentary layer, and when it does, what we say is the includer, which is the igneous, must have come after the includee, which would be the sedimentary rock. So if we had layers of rock, obviously they're going to be sedimentary, but then all of a sudden, and they're laid down, this is the oldest, second oldest, and this would be the youngest. But then all of a sudden, pressure from the earth causes an igneous intrusion to melt these layers, and we have a new layer of rock in here. We would say that this new intrusion would now be number 4, the youngest. So let's look at this. Here's an example. So we have 1, 2, 3, 4, let's say 5 layers. And the granite stops right here, okay? So what can we say about which is older and which is younger? Well, because the granite stops just before layer 4, we can't assume that the granite came after 4. So unless the igneous intrusion actually melts into the layers of rock, if it does, then like this picture I'm about to do, let's say this igneous intrusion or inclusion or intrusion, whatever you want to call it, it melts these. So here's layer 1, 2, 3, 4, 5. Let's order them if it did melt into the brick layer. Which one would be youngest then? Number 1, layer 1 would still be the youngest because the igneous intrusion didn't go up into 1, so we can't say it's younger. So then which would be the second youngest? We would say the igneous rock that came and melted these other layers. including layer 2 would be second, and then 2 would be third, 3 would be fourth, and 4 would be the oldest. So when we get igneous rock coming in to melt other rock, it gets a little more confusing. Let's try this one. Let's order them according to oldest to youngest. We have A, B, and C. Which one would be the oldest rock? Definitely A, so oldest, A. And then the second oldest would be B, and the youngest layer in this picture would be the igneous intrusion, which would be C. So C would be Y for youngest. Let's talk about geological time scale now. Geological time scale is broken up into eras and then periods, and it can even be broken down into smaller things. And in grade 8 or grade 7, we need to know the different eras. Right now, we are in what's called the Cenozoic era, which is time 0 to 50 million years ago. Before that was the Mesozoic era, and before that the Paleozoic, and then before that the Precambrian. So those are the ones we need to know. We also should be familiar with some important things that happened during each of these. For example, in the Mesozoic, the first dinosaurs appeared, but they also died out within that time frame, which was 250 million years ago to 50 million years ago. So within that time frame, dinosaurs appeared and then died out. The first flowering plants occurred in the Mesozoic. In the Paleozoic, we saw lots of things. The first amphibians, the first land plants, the first fish. In the Precambrian, the first skeletal elements, soft-bodied organisms also. And in the Cenozoic, humans came about. Okay, the first humans. Let's look at the brain pop on geological time scale, and then we'll get into some absolute dating.
Oh, cool, a fossil. Dear Tim and Moby, why do scientists name time periods like Jurassic and Precambrian? From Lila. Well, kind of to keep track of things. The planet Earth is extremely old, about 4.6 billion years. Lots of changes have happened over that time. The oceans have formed, continents have moved, mountains have risen, animals have evolved and gone extinct. To organize major changes, scientists have broken the Earth's timeline into sections lasting millions of years. This is called the geologic timescale. No, instead of millennia, centuries, and years, the geologic timescale is broken up into eons, eras, periods, and epochs. The Earth has had 4 eons, each lasting hundreds of millions to billions of years. Each of these eons is broken up into 2 or more eras, which are broken into periods, which are broken into epochs. All these units are of relative length, so they have no set number of years. The actual length of each unit depends on what geologic changes occurred in it. Like, one eon could contain a single era that's longer than another. For example, the Devonian period, when amphibians first evolved, lasted about 50 to 55 million years, while the Silurian period, which saw the first jawed fish, lasted fewer than 30 million years. Those names may sound confusing, but they usually have a pretty simple explanation. The Devonian period, for example, is named after Devon, England, where rock layers from that time were first studied. The basis for the entire timeline is a branch of geology called stratigraphy. That's the study of rock layers and the fossils contained inside them. According to stratigraphy, a rock layer, or stratum, is probably older than the layers above it, and younger than the layers below it. So, by studying the different layers, scientists can get a good idea of how animals evolved and how the rock composition of an area has changed over time. right, and they can also put everything into an order. Stratigraphy isn't perfect, though. Over millions of years, rock can break, bend, erode, and shift. To get a more complete picture of the conditions on our planet, scientists compare the strata from one area of the Earth to another. They also employ radiometric dating, which uses radioactive isotopes to date objects. As opposed to the geologic timeline's relative dates, radiometric dating gives an absolute date. Right now? Well, we're living in the Holocene epoch of the Neogene period of the Cenozoic era of the Phanerozoic eon. Hey, look at that! Weird.
Let's keep going. Let's talk about one more way. Absolute dating, as I talked about before, would give an exact date. And one technique scientists use is called radioactive decay. And it acts like a time clock. And so it's almost like a stopwatch. Radioactive isotopes of certain substances break down or decay into what we call daughter isotopes at known rates. For example, uranium-235, potassium, carbon-14. So one element basically changes into another. Elements that do this, well, potassium, rubidium, minerals that can be dated are biotite, and so on. Potassium atoms radioactively decay into argon. Think of an hourglass. Okay, it has potassium at the top, and then as it shifts down to the bottom, it becomes argon. Decay is usually at a constant rate. And so here's an example. Let's take something, all these atoms, let's say they're the parent material, and there's 12 of them. Okay, after one radiometric decay, you'll get half and as many that were there before. So now 6 of them turn into something else called the child or the new material, and you have 6 of the parent material. And so sometimes this takes 1,000 years to decay, and in some instances it may take 100 years to go half, and then another 1,000 to go half more. So notice this next round here. Okay, these 6 now go down to 3. So you divide the parent material in half again. Now you've got 3, one more, and now you have 1.5. And so it took 3 half-lives to get half as much material. So let's look at it again. So you start with 100% of your parent material, and after one radioactive half-life, you end up with 50%. After another one, you end up with 25% left over, and then 12.5, and then 6.75, and so on. So that's how it works. Every time a year goes by, whatever's left in the parent material decreases by 1/2. So here it is again. Carbon-14, for example. It takes carbon-14 5,730 years to go down 1 half-life. And so after 1 half-life, you've got half as much. After 2, you've got half as much again, and so on. Here it is again. Here's another example. The length of half-lives of an isotope depends. So uranium-235, it takes 4.47 billion years to go down by 1 half-life. However, thorium takes 24.1 days. Protactium, only 1.7 minutes. Radon, 3.8 days. Polonium, only 3.05 minutes. So it depends on the substance that you're using. So what can be dated this way? Most igneous rocks, metamorphic, some sedimentary. So let's see if we can do this. Yeah, we'll practice some radioactive decay problems in class. Thanks for listening.